Uh, Hello, am I audible? Can you hear my voice? Okay. Good afternoon, guys. This is the third class of our session, and I had some other commitments in the evening time, so that is why I needed to shift the class a little bit earlier. And I also don't expect much people to join because today is the final match is going on. But let that be. We'll continue our class. So let me share my screen. Can you see the screen? Can anybody respond?
Yes,
Okay, thank you. So I will start the class today. So this class will mainly discuss the contents of week 3, okay, and thereby we will discuss some problems based on the concept learned on week 3. So what was the main focus? So earlier we have already covered the isomers, constitutional, then conformational, isomers. What else we have done? Uh, so naming, drawing, or representation of conformers. Okay, and what else? Stability. So these all things we have learned. So in this week or today we are going to discuss about stereoisomerism. So what is stereoisomerism? So connectivity is same, connectivity of atoms are same, but arrangement in 3 dimension is different. And for that what we get? We get difference in optical response. So we'll all discuss it. Okay, how this affects the physical property of molecule. So mainly we'll start it today about we'll get some revision about chirality, then the definition, types, uh, then methods to determine, and also naming. These things we'll discuss today. So let us start. So I think you all have gone through the lectures. Okay, you have some idea. So we'll brush up. So chirality, okay, is a term. So where you have some molecule, you have two molecule which are non-superimposable mirror images of each other. Okay. So like I will show you a basic example. You have one methyl, then one NH2, then one COOH, and one proton. So this is a amino acid because you have this amino group as well as carboxylic acid group. This is a amino acid. If you do, uh, if you create a mirror image of this one, suppose this is your mirror. So just exactly opposite. So how it will look like? This is your H, NH2, CH3, and COOH. So you know that this solid bold line means it is top of the plane, and this dashed line it is below the plane. Okay, last class we discussed. Hmm. So this is exactly opposite. Uh, so this molecule B is exactly mirror image of A. Now let's say you have an axis here. You have a vertical axis through this, and you rotate it 180 degree. What should you expect? It will be superimposed into the earlier structure. If you do it, then what you will get? NH2, then your CH3 will come here, right? Then this this hydrogen proton, it will go backside, and this one COOH, it will come on the front. Just try to visualize it, okay, in your mind. So chirality or stereochemistry, you have to have a, basic visualization power. Okay, you have to see through the molecule and imagine the configuration or the conformation of the molecule in the space. Okay, you have to be little bit habituated with this visualization space. So if you try to focus it, it is very easy, you can realize it, and you will have no mistake in this kind of this nomenclatures and how to see the chiral molecules. You just need to have little bit of focus. So now you can see, if you compare this molecule and this molecule, is it the same? No. Why? Because see, amine and the methyl group are at the same position, but this proton and carboxylic acid, they have exchanged their position, they are not superimposable. Okay, so this kind of molecule, the relation between, suppose I am giving it A prime name, so the relation between A and A prime is called enantiomer. Okay, basically B and A prime are same, just a rotation. Okay, so or B, these are called enantiomer. They are non-superimposable mirror images of each other. So this is the basic criteria to show the chirality. This is the basic criteria. Now you can see one thing, in this molecule you have no symmetry elements. Okay, what are symmetry elements? As you all know, symmetry elements consist of mirror plane, okay, then uh, axis of symmetry, and then you have I, inversion center, then SN, that is called a rota reflection axis, alternating axis of symmetry. So in this case you need to consider this M. M means mirror plane. What is mirror plane? Mirror plane is a element of symmetry which divide, or better to say dissect, the molecule into two exactly similar parts. Okay, so suppose I have cyclohexane. Okay, so you know the how to represent in 3D. It's a chair form. Okay, now if you consider one plane, hmm, one plane I am considering, which is going from this carbon to this carbon. So you can see you have two exactly similar half. Okay, so more likely you can consider it like this. This is a mirror plane. You have one this up, you have one this up. So these are exactly same. So this is called a mirror plane. Okay, and it is called symmetric. Molecule is symmetric. Okay, now if I just do one thing, I give two adjacent carbon position, I will give two substituent. Then what it will happen? If you try to draw the molecule, so I'm not assigning any cis trans thing here, just normally. Let's say it is on the top and it is on the bottom. So now can you find any symmetry element here? No, because these two substituents are different. Okay, so here you cannot see any mirror plane here. So no mirror plane. Okay, so here this molecule is called chiral asymmetric. Okay, so chiral molecules should not have any mirror plane. Huh? If you have mirror plane, then what will happen? If you create a mirror image of this one, right? This is a mirror image. So if you just 180-degree rotate it, then it can be superimposed into this one. This is no longer non-superimposable. This will be superimposable. Okay, but this one, if you do a mirror image of this one, Cl and Br, now you rotate it 180-degree, so you can see it is not superimposable with the primary structure. Okay, that's the thing. So this is the basic idea. So we need to study the chirality importance of chirality. So it is a basic, you know, mm, basic property of molecules found in nature. So you all heard about orange and lemon. Okay, we daily consume these two fruits. Okay, so this orange and lemon, their the main ingredient is limonene. This is the compound. But limonene, this has two isomers. One is this one, and one is the other. Okay, so this is plus, this is minus. I will tell you about this notation later. What is the difference here? Basically, the structure is same, but the difference is in here, this carbon. The configuration of this carbon and this carbon is not same. Okay, one is R, one is S. That is the difference. So for this reason, this one smells different. This one smells different. Why this one smells different? Because this is one thing you should always remember whenever this is a basic thing about chirality. This always you remember that chiral molecule behaves similar in achiral environment, but behaves different in chiral environment. So this is like a rule of thumb. You should always remember this one in your life, that chiral molecules, if you put it in achiral environment, they will behave same. There will be no change. Only if your environment is chiral, then they can show the difference. Hmm. So we'll discuss it much time, much time during the class, so that you can have an idea. Regardless to anything, any effect, any measurement, anything, when your environment is achiral, then there is no difference between the isomers, chiral isomers. But when the environment is chiral, then your chiral compounds will behave differently. Hmm. So let us start. So the importance is a historical effect. So in 1960s, there was an accident on drug use. There was a drug that is called thalidomide. That time it was a USA approved drug, okay, for pregnant women. Why? Because it was used as some sedative medicine. Okay, but only they have two isomer of this compound. So whenever you are starting chirality, this one you should know that what is the historical effect. So this was the molecule. It is ketone connected to a chiral center. So you can see if your chiral center is sp3, most of the cases it will be sp3, then your carbon will be connected to four different groups. Okay, so we'll discuss a lot of time today. So this is one isomer, another isomer is this one. So okay, this was two isomers, so that are mirror image of each other, right? Now this one was the actual drug. Okay, but this other isomer was having negative effect on the newborn baby. So people could not study this much for, before that only they market, they sold the medicine in the market. So for that what happened in Europe and America, okay, more than almost 15,000 babies were born with defects. So you can see it is a generation that got affected by this effect of the drug. Huh? It is one generation. So that's how it was very important to study the chirality of drug molecules, because our organs and sensors in body are chiral. Okay, all the cells you have, many of the cells, most of the cells, and the systems inside the processes going on inside our body. So they all are based on this host guest mechanism. So these are also related to the chirality. Okay, some particular enantiomer will be reacting, some particular enantiomer will not be reacting. Okay, or it will react in an adverse way. So this is we should be very careful about. So now, uh, as I already have told you that for carbon sp3 atom, to show the chirality, it should be connected to four different groups. Otherwise, you cannot find the mirror plane in the system. Okay, so I already have just a second. I already shown you here, right? So you need to have four different substituent. Sometimes you also depict, sometimes this chiral center is also depicted as stereo center. Why? Because it gives rise to stereo or optical isomers. Okay, so we will dive further into this. So now how to name it, nomenclature. Okay, how to do it. So suppose you have this compound CH3, then NH2, H, COOH. This is our molecule. You can see these are all different fragments. Okay, so this molecule is chiral. You are sure about it. Now, first thing we have to do, have to numbering based on, okay, uh, atomic numbers. Okay, so first thing we have to do, you have to check, you have to prioritize the group. Okay, so the element that has more atomic number, it will be considered first. Okay, like in between these three, nitrogen, carbon, carbon and hydrogen, you know that nitrogen has the most maximum atomic number, so it will be termed as 1. We'll consider it as 1. Then after that, this uh, acid group, carboxylic acid group, and this methyl group, you can see carboxylic acid means C double bond O, OH. Okay, so this double bond O you can consider as 2 oxygen atom. So this carbon is connected to 2 oxygen and one more, that is 3 oxygen. So this is 3 oxygen and this is connected to 3 hydrogen. Okay, so which will be of more priority? This one, because oxygen has more priority than hydrogen. So if first uh, first atoms are same priority, go for next atoms. So this one will be 2, this one will be 3, and at the end will be 4. Now the rule is, wherever your fourth means the least priority group is there, you see from the opposite. So here you can see it is below the plane, it is dashed line. So now you have to see from the top of the plane, just opposite. You have to see from the top of the plane, and now you need to see the relation between 1, 2 and 3 groups. So 1, 2 and 3, you can see it is a clockwise rotation. Okay, so when there is clockwise rotation, it is considered as R. Hmm. So clockwise rotation R, and if it's anti-clockwise, that means S. So this R and S comes from some Latin words, rectus and sinister, that means right or left. Hmm. But you can simply keep in mind that clockwise R, anti-clockwise S. But it has to be from the opposite side where your least prior group is present. So from the opposite side of least prior group 4, right? So if the scenario is different, okay, so if you are given with this molecule CH3, which now hydrogen is on the top, and you have another group, suppose this is ethyl group. Hmm. Now ethyl group means CH2 CH3. So now you know that hydrogen will be 4, this is 4 already, oxygen will be 1, more priority. Now this methyl and ethyl group, here you see 2 hydrogen 1 carbon, here is 3 hydrogen, so this one will be more priority, this will be 2, this will be 3. Now you check the relation between 1, 2 and 3. 1, 2 and 3, they are rotating clockwise, it should be R, right? But no, this is wrong, right will be S. Why? Because your hydrogen is on the top, it is not on the downside. So you basically you should look from here, you should look from here, the opposite side. So if you see that 1, 2 and 3, it will be actually anti-clockwise, and S will be right answer. Okay, so you can remember it like this way. If least prior group is on the top, then reverse the configuration like that. This one you can remember as a shortcut. Okay, and if you have your least priority group on the plane, not on the back or on the top, then what you will do? Suppose this ethyl group, then you have hydrogen, you have one bromo, and you have CH3, right? So now what you will do? So if your visualization power is enough, then you can see it from here. Hmm? You just number it 1, 2 and 3. So this will be counterclockwise, this will be S. Okay, this is right answer, but you need to be little bit advanced before doing this one. So the general, you know, basic method is you swap it, double swap. So first I will swap this proton and methyl. Okay, I will try to take this proton into one of the position, either top or down. So I will take to the down position so that it will be more helpful for me. So it will be CH3 will come here, bromo will be in same position, hydrogen will go down. Now you cannot do negative, not negative, odd times. You have to do the even time, 2 time 4 time, like that. If you do odd times, then your configuration will be wrong. Okay, so uh, by one time doing, you have changed the configuration. Now if you try to get to the original configuration, you have to do one more time. Okay, so always try this one. event time swapping. So basically you can do it for 2 times, that will be enough for you to change this hydrogen position into one of the top or down. So for our you know more easy way, we have place it to the down. Now another one we have to swap. What we can do, we can swap this bromo and methyl. So methyl will be on the top, here will be your bromo, top of the plane will be methyl, and down will be sorry, hydrogen. Yeah, hydrogen. So now you can see 1, 2, 3 moving anti-clockwise, it will be S. So already I have written S here. So this one you can do if you have very good visualization power. So you don't need to go through these steps. Otherwise you do double swap and then you check it. Okay, just a second. Okay. Then this is fine. I have already discussed about limonene. Yes. Why? Chiral environment is important. So as I told you that chiral molecule will behave different in the chiral environment only. What are the chiral environment? It may be some measurements, okay, receptor or reactant, anything. See, some physical conditions such as light also. Yeah, light can be polarized. So, you know, CPL, CPL means circular, so circularly polarized light. So, uh, whenever you have a light source, suppose this is a laser, hmm, or a diode, you have a light source. So when light is radiated or getting released from any source, it will be like this. It will have different kind of polarization plane. So as you know, light has if light is propagating in such a way, it has different kind of wave. Okay, these are all standing waves. So this wave can be at any angle with the propagation of line, like this. So this, you have one plane here, you have another plane here, you have another plane here. So it has different plane. Okay, you have something like this, and then again it will go back to the original one. So this is called circularly polarized. Polarized. It will be like something. So if you have this and your wave function, there will be overlap of wave functions. So your light will go like this. This is the general representation. Okay. So now if you have something here that is called polarizer. What polarizer do? So only certain wave, okay, whose wave vector is along a certain direction, it will allow to pass, otherwise it will block. So if you have only this kind of wave, that has certain direction, wave vector that will be passed, so that after it passes you will only get this kind of polarization in one axis, and this is called linearly polarized light. You can understand it, right? It goes through a polarizer, and then the circularly polarized only converts to linear polarized because other planes are blocked. This is a filter, polarization filter. So this you pass through your sample. This is your sample. Normally, if your sample is achiral, the light transmitted will have the same plane. Incident and transmitted light will have same plane. But if your sample is chiral, then what it will do? It will rotate the plane of polarization. What you can see in the detector, here is detector. The detector will measure everything. So suppose this is your, uh, let me draw it in another color. Suppose this is your original plane of polarization, okay, and the light you are getting after transmitting from your sample is like this. You have an angle between them. This is called observed rotation from sample. This is a property. This is a property of chiral molecule to rotate the plane of polarization, and that's what I call it chiral environment. Circularly polarized light is not chiral environment, but when it is linear, then it is chiral environment. Okay, and your molecule reacts or interacts with it. Clear, right? So from there you can calculation is possible. Okay, so specific rotation, there is a term called specific rotation. Specific rotation always we express it in terms of wavelength, this light wavelength we are using, and temperature, which temperature we are using, because depending on your wavelength of light, okay, this value theta will depend, okay, also at the temperature. So these things should be constant, this lambda and temperature. And then you have alpha, this is observed rotation, unit is degree. On the downside you have C into L. C is concentration, gram per ml, and L is the path length. Path length is decimeter. So your sample will not be like a block or something. So you have a cuvette here. Suppose it is a cuvette, and your sample will be one solution, solid, anything in between it. Okay. So this cuvette has a path length. So this cuvette has a path length. Let's say 1 decimeter. Hmm. That's what. And then you can calculate specific rotation if you have the value of observed rotation that you can see in the experiment. You know the concentration of solution you have taken, and you know the path length or the diameter of your cuvette, so you can easily calculate the specific rotation. And then what you can do, you can get from here you can get the percentage of different isomers present, because this specific rotation is a fixed or constant for all. So one more thing I forgot to discuss here. So if your theta, is positive, okay, this is called d. If theta is negative, it is called L. D means dextro-rotatory and L means levo-rotatory. But D and L, D, D and L has no consequence with R or S. Mind it. We cannot determine any molecule is R or S from the measurement. So this measurement is called polarimetry. Okay, what is called polarimetry? We only get the value of the angle of deviation. So if it is positive, then it is dextro-rotatory. If it is negative, then that is L or levo-rotatory. But we cannot get any information about the exact configuration R or S. Okay. So suppose uh, you have mixture of two isomer A and B. Hmm. So A has different specific rotation, B has different specific rotation. Now you have, from the mixture, you are getting an observed alpha equal to something x degree. So now you can feed this data here, and you can get about the how much percentage of A or percentage of B is present. Okay, that thing you can do here, and you can also get value about enantiomeric excess. Enantiomeric excess. What is enantiomeric excess? So how much one species is more compared to to other. Okay, we'll try to do some exercise with this one so that we can understand, but that is later. Let us complete this part. Now determination and chirality case of more than one carbon atom. This is a practical problem, because you see in practical systems, or say some drug molecules inside our body, some natural products, they have a huge chain of molecules. They are not simple peptides or amino acids. They have one, two, or three, maximum four, five carbon atoms. So these have a long chain of carbon atoms, and within that they have lot of stereogenic centers and lot of chiral centers they have. So how to determine the chirality in case of the systems which have more than one carbon atom? Okay, so now you have to learn some trick, so that this is a general structure of a chiral, not chiral, as sp3 carbon. Okay, and this you can represent as, so if you look from here, just look from here, so you can visualize it as two carbon that is on the top. I will mark it 1, 2, 3 and 4. This is 1, this is 2, and this will be 3, this will be 4. You can relate this like I am seeing from this position, from this position I am seeing. 1 will be on the left, 2 will be on the right, 3 and 4. Now in this way, if you have your list positive like 4 group vertically means down the plane, okay, then your R or S configuration is same. This is case 1. Case 2, if least prior group is horizontally means top of the plane, then reverse the R is configuration. Okay, so we will see some example. Let us consider this molecule simple 4 carbon carbohydrate. Okay, so you can see you have 4 carbon here, and do you find any mirror plane here? I don't think, because this group is different, this group is different, so there is no mirror plane, and there are 2 chiral atom, these 2 chiral atom. Why? Because they have 4 different substituent. So let us first do for 1 carbon 2, right? For carbon 1, OH will be 1. Okay, now we have to compare between the CHO and the other one. So you can see this carbon is connected to 2 oxygen, 1 hydrogen. Okay, this carbon is connected to 1 carbon, 1 oxygen, 1 hydrogen. So this one will be your 2. 3 will be this one. Better I mark with different color. 1, 2, 3 and 4. Hydrogen horizontal will come later. Let us just see the configuration 1, 2 and 3. This will be looking like S, but hydrogen is in the horizontal position, so we should reverse it, so it will be R. So 1 R. For the second one, similarly you do let's say this is 1, this will be 2, this will be 3, this will be 4. 1, 2, 3. Look like S, but hydrogen is at horizontal, we need to reverse it. So this also 2R, 1R, 2R. This is how we should do it. So how many numbers of stereoisomers are possible for here? That is number of stereoisomer, total number 2 to the power n, where n equal to number of stereo centers or chiral atoms. This you remember. We know that here we have 2 carbon, so n equal to 2. Then in this case n equal to 2, then number will be 2 to the power 2, that is 4. Let us draw the 4 molecules, how they will look like. First one is, as we have seen already, H, OH, H, wait, and CH2 OH. Okay, this is not the same, but it's okay. Or I can write it the same only. Yeah. So now if I make a mirror image of this one, CHO, CH3. Okay. So these are two enantiomer, mirror images but non-superimposable, right? Then, so this will be R, R, hmm, this will be S, S. Now I can change one of the configuration in one of the chiral molecules, so it will be like CHO, H, OH, OH, H, CH3. Now take the mirror image of this one, CHO, OH, H, H, OH, and CH3, C and D. What you can see, these two are enantiomer. Hmm. These two are also enantiomer. But what is the relation between these two? Okay, or these two? They are not mirror image. They are not superimposable. These are called diastereomer. The diastereomer means non superimposable, non mirror image. Okay, they have no relation in between them. They are just normal isomer, no stereoisomer. Now uh, some of the compounds COOH, H, OH, H, OH, COOH. Okay, this is called tartaric acid. It has two other configuration, HOH, HOH, COOH, and the mirror image COOH, OH, OH, COOH. So one may be plus, one may be minus. So these are three isomers of tartaric acid. These two are optically active. This one is optically inactive. Okay, let us try to find out why. So can you tell me what are the RS configuration of the chiral centers? So 1, 2 and 3. 1, 2, 3. Hydrogen is in, so this will be R. This one 1, 2, 3. Okay, this one will be S, right? What for this one? Which COOH? This is S. Sorry, just a second. If this is R, this is also R. Yes, because it is rotating clockwise, sorry, anti-clockwise, should be S, but hydrogen is at horizontal position, should be R, and this one should be S. So this you can see R, R, S, S. Now let us check for this molecule 1, 2 and 3. Okay, should be S, but this is R. 1, 2 and 3 should be R, but this is S. So R, S. You can see the differences. Okay, these have one R, one S. This has both R, both S. What is happening? Suppose if R is rotating, R rotating positive angle, S will rotate negative angle. This is the primary thing of stereoisomers. If one configuration rotates a certain angle, the other configuration will rotate the same magnitude other side, like positive to negative. So here you have 50-50 R and S. So that is actually compensating. So that is why it is getting optically inactive. Hmm. Here there is no compensation. Both are R and both are S. That is why they are optically active. So one more way to look at it is you can try to imagine a mirror plane through the structure. What I told you, if some molecule has a mirror plane, then it will be optically inactive and it will be achiral. Hmm. This kind of compound is called meso compound, where we have this kind of mirror plane, and this R and S. So you can see there are presence of chiral center, but still you are not getting any chiral signal. Okay, so it is a very interesting topic, uh, racemization. So it is called racemization. Okay, now there are two types of racemization. One is called internal racemization. Just a second. Okay, so one is called internal racemization, another is called external racemization. So this is the situation where you have chiral centers present, but the molecule or solution behaves achiral. Why? Because somehow your individual chiral contribution it's getting cancelled. So what is internal? That's what I tell you. So you have a mirror plane out there. If you have one R and one S, they are cancelling each other. These two are cancelling each other. So overall you will get 0. Okay. And for the other one, RR and SS, if you have mixed both to a solution, okay, same concentration. This is suppose X concentration, this is also X concentration, and you mix them. So in solution they will be 50 into 50. That will be external racemization. This will be internally racemized. Both cases you will get 0. Okay, the deviation or the uh, chiral signal. This is very important. It will help you to examine a lot of experimental data. Then uh, how to separate chiral compounds? Again the same thing will come. Chiral compound behave differently in chiral atmospheres, right? So you need the same thing. So for separating normal compounds we generally do uh, chromatography, chromatography then distillation. What else you can do? Crystallization, and then precipitation. General method. But you need to have some chiral environment. What you will do? You will do chiral column. So you know about column chromatography? Anyone? Have you heard about the column chromatography? So
Yes, sir.
in column chromatography, we generally separate product in terms of what? Polarity, right? So there is a uh, you know stationary phase and a non-stationary phase. Just a second. Stationary phase. So depending on the polarity of your compound, you can choose to polar stationary or non-polar stationary, like that. And if you have the solvent, that is much more called a eluent. Okay, you can have solvent mixture so that you can run, and depending on the polarity, you can separate your spots. In chiral column, you pack this column with some chiral packing materials. Okay, so that it will allow R or S to pass. Okay, other blocked. Okay, like this. Then you can have precipitation. Precipitation. Suppose you have two amine. Say you have NH2. Then you have this one. This is your chiral center, and another one you have the other configuration, other isomer. This is the chiral center. And if you react with some acid, RCOOH, you can have two different adduct or the so what is formed in the reaction of acid base reaction, acid and base salt. So we will have one salt like this, H3 plus RCOO minus pH plus NH3 plus RCOO minus pH. Okay, but these two has different rate of crystallization or precipitation. So if you take it in a solvent, take the dissolved solution, one will be crystallized, one will be staying in the solution. So differential solidification, and then you can separate it. Okay, so now we need to see some of the cyclohexane that we cycloalkanes that we studied the last class with the chirality. So how to represent chirality, also determined in cycloalkanes. Let's say we have this one. This is cyclopentane. You have methyl and OH group. Okay. How you can represent it? So these are both on the top of the plane, right? This is cyclopentane structure, top of the plane, methyl and OH. So you can draw a plane, right? So this will pass through here, this will pass through here, and it can, just divide the molecule into exact half. Okay, so you have a mirror plane, and that is why it will be achiral, no optical response. Similarly, if you have instead of this one, if you have this, okay, what will be the scenario? Just draw it once. You have one methyl on the top, one OH at the bottom. But now you can see that you don't have any mirror plane, right? Okay, just a second. Okay, so you can see there is no mirror plane here. So it should be chiral. Okay, so there are two chiral centers present here. Now similarly, you can have another comparison. Let's say you have this molecule which is cis and another one is trans. So based on the previous idea, what you can observe that here you have a mirror plane. You can divide it into exact half, so it will be achiral. But this one you don't have any mirror plane out there. This one will be chiral. Let us go to the cyclohexanes. How to represent in cyclohexane? Let's say you have this compound. Okay, how can you represent this one? Draw a chair from of cyclohexane. So you have exactly opposite 1, 2, 3, 4. 1, 4 position. So 1, I'll give one CH3 here down. 1, 2, 3 and 4. It is on the top, which you can clearly see you can have a mirror plane right here. Okay, it can divide your molecule into two halves. So you have a mirror plane, and that's why it will be a chiral compound. If you draw the other one, if I just change it, CH3 OH, I think this one also will be a chiral. The same thing, you can even draw a mirror plane in this way. If you change the position, okay, if you change the position from 1, 4 to 1, 3, suppose you have CH3 here, here you have OH, what will it will look like? Draw it. CH3 is in the downside, 1, 2, 3, OH is also in the downside. There is no middle plane, right? So if you try to do something like here, but here OH and CH3, they are not same. Okay, so this will be chiral. Then one more effect needs to be discussed, that is uh, external compensation or racemization through bond rotation. Which bond? Single bond, sigma. Let us take the example of butane. Okay, so in butane you have three types. You already know, but still I will discuss. Three kind of conformation. So this is a Newman projection I am drawing. CH3, H and H. You have this one. This is called Gauge staggered. This is anti-staggered. This is also another gauge staggered. Now, if you can see, these two doesn't have any superimposable mirror image relationship. This one. So this is called diastereoisomer. These two. Same. This one and this one are diastereomers. But these two, this one and this one, it is a mirror image, right? It is a mirror image and non-superimposable. So these two are non-superimposable mirror image. So what we call them? Enantiomers. Okay. So what is important here is that you see you don't have any chiral center present because butane CH3, CH2, CH2, CH3. You don't have any chiral center present, right? There are no chiral center, but still it can show some chirality because of the conformation. So that gives rise to the thing called conformational chirality. So what we have learned till now is called point chirality. uh, that involves a center or an atom based on which we decide the chirality. But there are some system where you don't have any chiral center but still you will have some chirality. You know about DNA. So how DNA looks like? So it's a coil, okay, intercalibrating coil like this. DNA has a helical chirality. You know the structure is called helix, DNA helix. You have different kind of B DNA, A DNA, Z DNA. So this is called helix kind of structure. And these structures also have the chirality that is called helical chirality. These are all conformational chirality. You don't have any chiral center, but still you will get some chirality. A similar one example I can show you. I think you have know about this one. So this is a conjugated ring. This is a conjugated ring. So these are all phenyl rings. And then what happens? This phenyl ring, it cannot go in the same plane with the other one. So one of these phenyl rings stays on the top, this one stays on the bottom. Let me write with another color. Stays at the bottom. So these are called conformational measurable chirality. Okay, we understand, right? Then following the same way, what are diastereomer? Already discussed. Don't have mirror image. Relationship. Don't have superimposable ability, right? So sometimes this double bonds, say CH3, CH3 and this one CH3 CH3. So we call it as cis and trans, right, from the geometry, relative geometry of the double bond substituents. These are also can be called as diastereomer because they don't have any optical relativity. And there is one more interesting term that is called atrop isomer. So this is also same like conformational isomer, okay, but optical isomers or enantiomers generated by by hindrance of rotation, hindrance of bond rotation. Suppose you have this kind of group. This is a phenyl ring. This is also a phenyl ring, but this is in the plane of the paper. This is vertical to the plane of paper. You have a big group here. You have a big group here, and here also you have a big group. Here I have a big group. So then they cannot rotate. Cannot rotate. What happens? Even you have this single bond, still they cannot rotate because of these big groups. They are a steric hindrance. Okay, so they can form two isomer. Okay, so these are called atrop isomers. Okay, so with that, I think we have discussed all the concept for this class. Okay, one more thing is pending. So like this double bond, you have another class of compound that are called allenes. Allenes are more than 3 carbon that are connected in double bonds. So it will be like say C double bond C double bond C, okay, or C double bond C double bond C double bond C. So these actually, so you know that for normal sp2 carbon, hydrogen, hydrogen, and then you have another carbon. But if you need to do another pi bonding here, then it will not be in the same plane. So this one will be like this. This one will like be this. This only for odd cases. If you have even cases, so I'll just a second. I'll wipe this up. I'll write it here. For even cases, this is 1, 2, 3, and 4. In that case, it will be in the same plane. But if it is odd, 1, actually maybe I'm wrong. For odd cases, yes, for odd cases it will be in the plane, but for even cases it will be out of the plane. Okay, so here you have a mirror plane. This is your plane. Okay, but this one you can consider it as, if you view through this angle from this side, you can see two hydrogen that is coming on the top, okay, and two hydrogen that is going behind. Okay, and the numbering will not be the same. So the proton that will be close to you, that will be numbered first, 1, 2, and then you can number it as like this, 3, 4. So just for simple cases I am doing hydrogen, so you can have different R groups present here. carbon, halogen, any group you can be present. This is how you should do the RS nomenclature. Okay. So with that, let us do some question practice. So first question is that one molecule is given. Let me draw it. You have one proton on the top. Here you have methyl group, and here you have double bond O. So what is the configuration of the chiral center? This is the question. Options are R, B, S, C, no stereo center, and D is cannot be determined. So can you try it?
R configuration.
Okay. Yeah, it is right. So I can show the others how to do it. So basic thing is that you need to number this one oxygen, then this carbon is connected to 3 hydrogen, but here it is 2 oxygen 1 carbon, so this will be second priority, this will be third, hydrogen will be fourth. 1, 2 and 3, this is anti-clockwise, should be S, but hydrogen is on the top, you have to reverse it, so it will be R. This one will be correct. Okay. Now second question is that a molecule can be D or L based on, there are four options. So D should be related to R, L should be related to S, D should be related to S, L should be related to R, D and L measured from polarimeter, no direct relation with either R or S, and D option is D and L measured from single crystal XRD. These are four options. So what is the right answer according to you? Any idea?
Option C, sir.
Option C. Yeah, it is right because uh, D and L is the angle of rotation of plane polarized light. Okay, and we don't know the exact RS configuration, and to know this exact configuration we need XRD. So XRD is required for getting information on RNS. So that question is What is this? Okay. So you have four compounds. Just a second. Yeah. You have four compounds given. You have to tell that one is different from other three. So which one is the odd one? One, two, three, four. Rule out the odd one. So this is basically same molecule with different configurations. Hmm? So you have to rule out the other one. Three configuration will be same, one will be different. Can you tell me?
Option C, R configuration.
Option C is
4, sir. Option 4.
okay. Okay, let us do it and then we can see. So for this one, you can number it. Beer will be 1, then Cl, then ethyl, then hydrogen. So 1, 2, 3. Okay, this look like S, but hydrogen is in horizontal position. Okay, it will be R. Then 1, 2, 3, 4 look like S, but hydrogen is in horizontal, so it will be R. What is for this one? 1, 2, 3, 4. So hydrogen is already in the vertical position, so we don't need to change. So this look like S, right? Then for this one, 4, this is 1, 2, 3. Okay, this look like S, but it will be R. So you can see 1 is R, 2 is R, 4 is R, but 3 is S. So it is different. So right answer will be 3. Okay. So as I told you, so this one you should consider it as like this. Horizontal will be on the top and vertical will be on the downside. Now you give the numbering, and as your fourth priority list priority is on the top, so you have to reverse it after that. So it looks like S, but after reversing it will be R. Clear? So we go to the next question. A molecule is given like this. You have a cyclohexane ring after that, and here you have some stereo centers present. Sorry, this will be the solid line, top of the plane. So you have to tell number of stereo centers present and then number of stereo isomers. Okay, there are two questions. Can you try?
Two stereo centers and four stereo isomers.
Where are the two stereo centers? It is this one, right? On the
Yes, four different groups.
cyclohexane ring, these two, right?
Yes.
Yeah. So this is another one separate group, this is separate, and this one separate, and their proton is there. Similar for this one also. So two stereo centers and number of possible stereoisomers, that is 2 to the power n, right? So in this case, number of centers is 2, 2 to the power 2, that means 4. This will be right answer. Then you are given with two compounds, you have to tell the relation between them. This is one, okay. So you need to tell the relation between A and B. Your options are A, that is identical, that means the same compound. B will be diastereomer, C will be enantiomers, and D will be meso compound. Can you tell me what is the relation?
Identical.
Identical. Okay, let us see.
Sir, explain yourself.
Sorry.
Please explain this question.
Yeah, sure. So before doing that, we need to get this molecule at similar orientation, okay, or similar projection. So as this is this 1, 2 and 3 are like this, so we'll just rotate this one first so that we can get to the similar position. So if you rotate it, then in this position hydrogen be on the top, then bromine on the bottom, then here hydrogen on the bottom and bromine on the top. Okay. And now you need to find the relationship. So let me just draw a mirror image of this one. So I am doing in reverse way. See, if I draw like this and bromine and then and hydrogen. Now you just see, this is 1, 2, 3, 1, 2, 3. Is it same? Bromine is on the top, hydrogen on the bottom. Bromine is on bottom, hydrogen on the top. So this is same molecule, like these are identical. Okay, but this is the mirror image of this one, of A. This is mirror image of A. Okay, so now you can see that B is the mirror image of A, and they are non-superimposable, so they are enantiomers. You got it?
No, sir.
Yes, sir.
Okay, first what I did, I draw the exact mirror image of A. Okay, then you can see H, Br and BRH, like the axial and equatorial positions. You can see, you can understand this part, mirror image, right? And this compound that is given B, that I have rotated, you know, how much, 120 degree almost. So then, so this is my 1, 2 and 3. I have rotated so that my 1 position is here, this 2 position has come here and 3 position come here, but the relative is same. So at 1 position, see, bromine is in the equatorial part, hydrogen is in axial, it is in axial. 3 position, hydrogen is in equatorial, bromine in axial. Okay, now I compare between this mirror image and this rotated form. You can see this is same compound, identical. 1 position, bromine is on the equatorial, hydrogen is bottom, axial. Third position, 3 position, bromine is axial, hydrogen is equatorial. This is same. So it is exactly matching with the mirror image. Now you can get it.
Yes,
Yes,
sir.
sir.
So that is what. So you have to, uh, you know, get the confirmation in similar way. So your 1, 2 and 3 carbon, it is on the front, on your side. So this one also you have to rotate it so that you can have these 3 carbon on the front side. Then you can compare it. Okay, otherwise it will be very difficult. So there is a little bit of tricky question. So you just have to rotate the molecule so that you can compare it properly. Once if you can do it, then it will be of no, worry. Next question. So a calculative question. What is that? Okay, one more question. So uh, choose the correct statement on diastereomer. Okay, number 1 is magnitude is same, sign and rotation is different. Then non-superimposable mirror image of each other. Hmm. She is different in physical properties, and D is can be interconverted through rotation of bond. So there are 4 statements. You have to choose the right one about diastereoisomer.
Different in physical properties.
Okay, so I'll try to discuss all of the options. So magnitude is same, sign and rotation is different. This is for enantiomer. Okay, you have D and L. Non-superimposable mirror image of each other. This is also for enantiomer. Okay, can be interconverted through rotation of bond. This is also enantiomer. We we discussed the butane, example of butane. So this will be the right option. They are different in physical properties. Okay. So one more thing I forgot to discuss. So butane, you have this two isomer CH3, H, H, CH3, H. I will not draw the anti one. I will only draw the Gauch 2. you have the mirror image, this one. Okay, it is also gauge, it is also gauge. They are mirror image of each other and they are enantiomers. So we should expect some chiral nature expected but not observed. Why? Because of the rapid interconversion through bond rotation. And you know that this antiform is CH3 H H3 H. This antiform is much more stable, huh? Much more stable because it is lowest in energy. We discussed it in the last class. So at room temperature not observable. But if you go to low temperature, sufficient low temperature, then you can see some effect. Because at low temperature your bond rotation gets freezed. So how bond rotate? It absorbs some microwave energy and it rotates, right? So at low temperature you freeze that bond, it cannot rotate. So if it is at some moment in a configuration where it can show some chiral activity, then you can see it. And how you can observe? So what are the measurements you can do it? Obviously polarimetry. Along with that you can do NMR, XRD, these things at low temperature to get an information. Okay, so today we'll stop it here. So we discussed about the general idea of chirality and some of the questions we practiced. And if you have any questions, you can in future let me know so that I can discuss it once again. Okay, so I'll unshare it today, and all these lectures I will upload and the study material also. So okay, all the best. Thank you.
Thank you, sir.